The sinking of the Titanic can be attributed to any number of failures. Currently, there are two popular explanations as to why the Titanic sank regarding the materials of the hull. The hull was composed of steel plates held into place by iron rivets. The failure of both of these materials is what led to the tragedy of the Titanic. The steel of the hull was found to have higher levels of sulfur and phosphorus than most modern-day steels, as shown here. The hull also had significantly less manganese than what is currently in use today. Manganese is used as an alloying agent to increase the hardness and strength. With less amounts of these elements in the steel composition, the overall toughness of the hull was weakened. Samples taken from the hull of the Titanic also found that the steel was produced using air cooling and was unannealed. This can be seen in the microstructure. It was found that the steel in the Titanic's hull was a ferrite and pearlite composition, with long, coarse, pearl-like structures. The figure here shows a comparison between modern-day steel versus the steel taken from the Titanic's hull. A coarse, pearlite microstructure often lowers a material's toughness, which would have contributed to the hull's fragility. Shown here is another image of the microstructure of the Titanic's hull taken from a different sample. This image shows the presence of pearlite but has significant differences to the other samples taken. This may indicate a variability in the overall structure and properties of the steel of the hull due to inconsistent manufacturing of the steel. This variability shows that some parts of the Titanic may have been fine in the cold temperatures, while other sections would suffer. The temperature of the water during the Titanic's voyage has been estimated to have been around 28 degrees Fahrenheit or -2 degrees Celsius. This temperature would have contributed to a ductile to brittle transition in the steel's hull. The graph here shows data taken from an impact test on a hull plate in the longitudinal direction, a hull plate in the transverse direction, and on a modern-day steel similar to what was used on the Titanic. The test shows the samples from the hull have a transition temperature of around 40 degrees Celsius and 70 degrees Celsius respectively, and the modern-day sample had a transition temperature of -15 degrees Celsius. The high transition temperatures of the samples indicate how the hull became embrittled while sailing through the freezing waters of the Atlantic. This ductile to brittle transition would have played a large part in the damage taken from the iceberg. It has been found that manganese content affects the ductile to brittle transition temperature in metals. This makes the data consistent with the chemical composition of the hull, which found low manganese percentages in the samples and higher phosphorus levels, which also plays a role in the transition temperature of a metal, overall resulting in the higher transition temperature shown. The data shows the results of tensile tests on samples taken from the Titanic's hull. Both samples have a consistently low % elongation, indicating that the hull was brittle and had a low ductility. While the yield stress indicates a tough material compared to other types of steel, it can be considered low. Another major contributor to the Titanic's sinking is the rivets that held the hull plates in place. The rivets were composed of an iron silicate material. The rivets were driven into the hull and flattened or squeezed on the inside. Samples taken from the Titanic have found that many of these rivets snapped upon impact with the iceberg, which led to water breaching the hull. This figure shows the microstructure of one of the rivets from the Titanic. The rivets were wrought iron composed of iron silicate slag. An analysis of a rivet found it was composed of over 9% of the slag. This is over 3 times the expected amount and greatly impacted the strength of the material. The orientation of the microstructure within the wrought iron also greatly impacts the tensile strength. If the iron is in a parallel direction to the silicate slag within, then the tensile strength is considered high for the material. But in the case of the Titanic's rivets, analysis found the microstructure to be perpendicular, which negatively impacts the integrity of the iron. This creates a large amount of space within the material that is susceptible to fracture. Likely this is the case as to why many of the rivets were found to have been snapped or fractured in the wreckage of the Titanic. At the same time the Titanic was being built, her sister ship, the Olympic, was also being built with the same materials, including the same wrought iron used for the rivets. The damage found on the Olympic would be consistent with that of the damage on the Titanic. This image shows the damage to the Olympic's hull after a collision with another ship. In the image, you can see many of the rivets missing. It was found that they have a tendency to pop out of the holes after the head snapped off after collision. This indicates a failure of the metal and its tensile strength. In conclusion, while the steel used for the Titanic may have had a high tensile strength and toughness for the time period, it was not adequate for the conditions it would be used in, resulting in a material failure. The steel used had a low fracture toughness that resulted in brittle fracture of the material. The metal could have possibly been heat treated to improve the toughness instead of just being air-cooled and annealed. Perhaps with heat treatment, the metal could have withstood the temperatures of the water, and the tragedy of the Titanic could have been avoided.